part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss Poynting's theorem, which pertains to conservation of energy. And over the next few lectures, I'll also be discussing conservation of momentum and conservation of angular momentum as well. But first, I want to begin with a statement of conservation of charge. And we're interested in a local statement, which is a much stronger conservation statement than global is. Okay, so we have a certain amount of charge Q, and that's in a certain volume. So that is equal to the volume integral over the volume charge density. And again, Q is a function of time, and also, of course, your volume charge density is a function of time as well. The amount of current that flows out of this volume is equal to minus the surface integral of the volume current density and actually the normal component of the volume current density, normal to the surface over which we're integrating. Okay. I can also take the derivative of this expression with respect to time, and that'll be equal to the volume integral of the partial derivative with respect to time of the volume charge density. Now notice here, of course, I dropped off the arguments. By means of the divergence theorem, I can convert this surface integral to a volume integral. So this is minus volume integral of the divergence of the volume current density in d tau. So therefore, this expression must be equal to this one. But since this has to hold for arbitrary volumes and not just one volume in particular, I can say that the integrands must be equal to each other. And therefore, we have the divergence of the volume current density is equal to minus the time derivative, or partial derivative with respect to time of the volume charge density. And that's conservation of charge. And of course, you'll recognize it from before. We've already encountered it. But before, we called it continuity equation. Okay? That's conservation of charge. Leave it at there just for one more instant, and then we'll move on. Way back in electrostatics, we came up with an expression for the amount of work done or required to assemble charges. So that's equal to epsilon naught over 2 E squared. So epsilon over 2 volume integral of the electric field squared. We also wrote down an expression for the amount of work required to get currents going, and that was the amount of work that had to be done against the back EMF. That's equal to 1 over 2 mu naught volume integral of the magnetic field squared. So together, we have the amount of electromagnetic energy stored in the fields. it's useful at this stage to introduce the energy density. Which we'll denote by a lowercase u, and that's equal to epsilon naught over 2 e squared plus 1 over 2 mu naught b squared. Okay, so we want to calculate the work done on the charge by the fields. And you know the drill. What's work equal to? Well, it's force times the displacement over which the force acts. And the force that we're talking about in this case is the Lorentz force, or we're going to make use of the Lorentz Force Law. So this is QE plus QB cross B. And we can rewrite the line element as velocity times time differential. Okay, so you notice the second term is going to drop out because we have V cross B, and that's dotted into V, so that is always going to be 0. Whenever you have two vectors, or a vector appearing in an expression like this, so we'll be left with Q, E, dot V, dt. But I want to rewrite this and put it in a little bit more useful form. So I'll recall that the amount of charge is equal to charge density times flowing element, and also the current density is equal to the charge density times velocity. So with these two relations, I can rewrite this expression to give me the rate at which work is done. That's equal to volume integral of the dot product of the current density and the electric field. So we would like to get an expression on the right-hand side that's solely in terms of the electric field and magnetic field. And to do that, I'm going to have to make use of several of Maxwell's equations. Anyway, we have, and we don't have to write down, we want to have divergence of the electric field is equal to the charge density over epsilon naught. We're not going to need that right now, but I just threw it up there anyway. And we also have magnetic field is divergence free. Again, we're not going to make use of that right now, so just for reference. Now the two bottom equations, we will use Faraday's law. Curl of the electric field is equal to minus the time derivative of the magnetic field. And on the right-hand side, we have the curl of the magnetic field is equal to mu naught times J. And we may not be able to read it because it's scrunched up. Plus mu naught epsilon naught, partial derivative of the electric field with respect to time. That, of course, is the displacement current, and this is our true current. And remember when we were talking about Maxwell's equations and displacement current, he said if you really want to be picky about things, you really ought to only have the true sources on the right-hand side, and basically you want to view these as coupling terms, the partial derivatives with respect to time. But for calculational purposes, it's more convenient right now. Okay, so anyway, we see that we can substitute in for J by using the Maxwell Ampere relations. So I will write this as derivative of, or the rate at which work is done is equal to mu naught curl of the magnetic field down into E minus epsilon naught volume minus epsilon naught volume integral over the partial derivative of the electric field with respect to time dotted into E. Now I still need to do a little bit of work here, so I'm going to make use of this identity that we counted many months ago. And basically the divergence of cross product of two vectors is equal to remember, this holds for any two arbitrary vectors, not just electric field and magnetic field. I will read it off. We've got the divergence of the cross product of the electric field and the magnetic field is equal to the magnetic field dotted into the curl of the electric field minus the electric field dotted into the curl of the magnetic field. So I'm going to use this expression to get rid of this term here. I'll read it off. 1 over mu naught, volume integral of dot product of the magnetic field and the curl of the electric field minus 1 over mu naught, divergence of the electric field crossed into the magnetic field minus epsilon naught, dot product of the electric field and partial derivative of the electric field with respect to time. I'm going to make use of Faraday's law to rewrite the curl of the electric field as minus partial derivative of the magnetic field with respect to time. And I'm also going to write down one more expression. If we take partial derivative of E squared with respect to time, that's equal to 2 times partial derivative of the electric field with respect to time dotted into the electric field. So I can make use of this relation to replace this integrand, and I can do the same thing for the magnetic field as well. And therefore, I will wind up with, I have derivative of work with respect to time is equal to minus derivative with respect to time of the volume integral of B squared over 2 mu naught plus epsilon naught E squared over 2. And then my final term is minus 1. And I want to put 1 over mu naught out front here. Divergence of the electric field and the magnetic field, and we integrate this over the volume in question. I can convert this last integral to a surface integral by means of the divergence theorem, so I'll just leave this up here for one more instant and minus 1 over the surface integral that balances volume 1 over mu naught cross product of the electric field and the magnetic field dotted into the normal of the surface over which we're integrating. So this is Poynting's theorem. To understand this in terms of conservation of energy, you need to make explicit what each of these terms represents. So on the left-hand side, again, we have the rate at which work is done, on charges. This first term on the right-hand side is the time rate of change of energy stored in the fields. And this last term over here represents the rate of energy transported out of the volume. And there's a special character for that integral. That's 1 over mu naught times cross product of the electric field and the magnetic field. This is the Poynting vector. And it represents the energy flow per unit area per unit time. Write this expression a little bit more compact form. If I realize that I can write the rate of work being done as a volume integral over the, we'll say, energy density of the work being done. And I can identify the second term. We should have this as derivative with respect to time. So I can remember that this is actually the energy, electromagnetic field energy density here. And pull this term on the left-hand side. This right-hand term, I'm just going to go ahead and stick this back in the form of the volume integral. And because, again, this has to hold for arbitrary volumes, we wind up with the partial derivative the mechanical density term plus the energy density term of the due to the electromagnetic fields is equal to minus the divergence of the Poynting vector. So that is a statement of conservation of energy in differential form. Okay? And I'll put it up there for another moment before we move on. first example that I'm going to work through is that of the amount of power dissipated in a segment of wire. Okay, so we have a certain current flowing. This is maintained at a potential difference. So we've got 0 over here and some potential V over here. So we've got a uniform electric field in the wire, and we'll assume that it's of length L, and we'll assume it's of radius R. I want to figure out what is the Poynting vector first of all. Well, magnetic field due to a long straight wire, and we're just looking at one particular segment of that wire, that's just equal to mu naught I over 2 pi s in a circumferential direction. The electric field, which is uniform in this case, is just equal to potential difference over the length of this wire, and that'll be in the z direction. So when I take the cross product of these two, I'm going to wind up with a Poynting vector that it'll be in the radial direction and pointing inwards. The question is that we're going to figure out how much power is dissipated. So we look at the Poynting flux term. So this is going to be uniform. We're integrating over the surface of the cylindrical segment of wire. Basically, this is just going to be equal to IV. Mu naught's going to cancel out. And we've got 2 pi s over L. And evaluating the surface area of the cylindrical surface, that's also going to be a 2 pi s. L actually be the radius, so really we want to say 2 pi r L. And therefore that's just equal to IV. That's the amount of energy or power that's going to be dissipated in this wire. So we can figure this out using the Poynting vector. The interesting thing here is that this is from the fields outside of the wire. Okay, back in when we first started talking about EMF and Ohm's law, I mentioned that the energy was transported outside, so transmitted inside the wire, as appealing as that idea might be. Okay. The second example that I'm going to work through is determining the power that's transported down to coaxial cables. We'll assume that they have inner radius or inside radius A and outside radius B. Assume that the current flows one way down the inner cable and the other way down the outside cable. I want to determine the power transported so that means I need to know what the Poynting vector is. To figure out the Poynting vector, I need to figure out what the electric and magnetic fields are going to be. We'll assume that these two cables are held at a potential difference. And basically, we encountered this problem a long time ago regarding the electric field, because if you have a long straight wire that carries a line charge density, electric field is equal to 2 lambda over 2 pi epsilon naught s in the radial direction where lambda is the line charge density. the magnetic field in this case is equal to mu naught I over 2 pi s in a circumferential direction. So you see that when you take the cross product of these two vectors, you're going to wind up with power being transported along the cable. So we want to figure out the power transported, therefore magnitude of S is equal to lambda I over 4 pi squared epsilon naught S squared, and this is a long wire. Power is equal to this Poynting vector evaluated over some surface. So basically the surface in question is, well, the power is going along the wire, so it's going to pass through this basically an angular disk. We'll integrate from 0 to 2 pi. And also, we'll integrate radially from A to B, and that'll be ds over s. And the reason why, remember, of course, that your surface element is equal to s ds dphi. So one of those s's cancels with the one in the denominator. Therefore, when you do the math, you wind up with lambda I over 2 pi epsilon naught natural log of b over a. Now, it would be a little bit more useful to put this in a slightly different form. In other words, in terms of the potential rather than in terms of the line charge density. So just as a reminder from way back in the old days in electrostatics, remember we integrate minus the line integral of the electric field from some reference point, which we're taking as the outer cable, to some final destination, which is your inside cable. When we do that, that's going to be minus b to a, or we can flip it around, and that'll be a to b of lambda over 2 pi epsilon naught s ds. And that's just equal to lambda over 2 pi epsilon naught natural log of b over a. And substituting this in here, we wind up with a current times the potential, which is just the power that is transported in this system. Okay? I'll leave it up there just for a minute, and then we'll move on to the final example of the day. And this final example is based on a paper published by Mark Heald in the American Journal of Physics back in 1984. So in this case, it's going to be less of me working through the math and more of you looking at the simulations. So let me just set the problem up. Here we've just got a battery hooked up to a resistor. Now, I've discussed this problem before when we were talking about surface charges and the role that they play in circuits. It was basically the discussion was on bridging the gap between electric fields and also on circuit analysis. Okay, so what Heald did here was he took this circuit and modified it and essentially turned it into a two-dimensional problem, and therefore I could use Laplace's equation to solve for the potential and the electric field. So what I'm going to do is I'm going to go ahead and show you what I mean by that right now. So let's look at a simulation. Here's a simple DC circuit composed of a battery and a resistor. and it's drawn as it would be in a textbook. The hookup wires, possibly composed of copper, silver, or tin lead alloy, form a rectangle. This is purely for aesthetic reasons. Next, we distort the hookup wires into a circle. As long as we're dealing with a DC circuit or slowly varying AC, this changes nothing as far as Kirchhoff's loop rules are concerned. Next, we make some assumptions to facilitate the analysis. Suppose we treat the resistor as if it were distributed along the hookup wire rather than being confined to a component. We're going to replace this real system with a two-dimensional model. By two-dimensional, I do not mean that the circuit is sitting flat on a laboratory bench, rather that the circuit is replaced by a stack of an infinite number of circuits. Now we imagine that the current can be treated as a current sheet. This greatly simplifies the analysis. The magnetic field, then, is simply that due to a solenoid. It is uniform and directed along the axis inside the cylinder, and it vanishes outside. The black line on the left-hand side of the cylinder represents the location of the battery. In accordance with Ohm's law, the potential on the conductor is V0 phi over 2 pi, where phi ranges from minus pi to pi. Let's assume the radius of the cylinder is r. The two-dimensional Laplace's equation can then be solved, and the potential can be expressed in closed form. V interior is equal to V0 over pi inverse tangent of y over r plus x. The exterior potential is V0 over pi inverse tangent of ry over x squared plus rx plus y squared. Light green corresponds to high potential and blue to low potential. The equipotentials are straight lines inside of the conductor. Once the potential is obtained, the electric field can be calculated. The electric field, as you'll recall, is equal to minus the gradient of the potential. All electric field lines in this situation are arcs of circles. One feature of the electric field might trouble you. Notice that the field lines do not leave the conductor normally, rather they are diagonal. This is because we not only have the electric field due to the surface charges, but we also have currents as well. Finally, we see the Poynting vector depicted. The surface charges drive the conduction current, but they also create the electric field that gives rise to the Poynting flux. The Poynting flux is perpendicular to the electric field and the magnetic field. Hence, the lines of Poynting flux lie on equipotentials, and they represent the transported energy from the battery to the resistor. In this simplified two-dimensional model, the Poynting vector vanishes outside of the circuit. In a three-dimensional model, which is a more accurate representation of the physics, the Poynting vector will not vanish outside. For more information on the role that surface charges play in circuits and on the Poynting vector, see the BocaPhysics website for a list of references.